Let us continue oxygen family. In the oxygen family, we will go for sulfuric acid properties. Sulfuric acid, you might have seen in the laboratory, it is colorless. Concentrated sulfuric acid, if you see, it will be like oil. It will be just like oil. How means dense oily liquid, we will say. So sulfuric acid, we will say as concentrated sulfuric acid, dense oily liquid, we will say. Sir, sulfuric acid is having a higher boiling point, higher viscosity. Why is it so? That we will see. Now we will take sulfuric acid. In sulfuric acid, sulfur is there and 4 oxygen atoms are present in the sulfuric acid. Sulfuric acid contains 2 hydrogen atoms. It is oxo acid. It is oxy acid. Therefore, both hydrogens present in the form of OH group. OH group like this. This sulfur is making double bond with oxygen and here single bond. Why? Because this oxygen already having one bond. It is sulfuric acid. Now we will take another sulfuric acid. Another sulfuric acid we have taken. Now you say between this oxygen and this hydrogen, what bond is possible? You see, hydrogen bond is possible. It is going for neighboring hydrogen bonding. It is going for hydrogen bonding with the neighboring molecule. Here also hydrogen bond, here also hydrogen bond. Because of hydrogen bonding, this sulfuric acid is having high boiling point and high viscosity. Okay. So due to intermolecular hydrogen bonding, it is having high viscosity and high boiling point, we are seeing. Sulfuric acid is a dibasic acid. Therefore, it can give 2 H plus ions. So it will have 2 Ka values. Sulfuric acid is having 2 Ka values, Ka1, Ka2. How Ka1 and Ka2 will be there? Sir, Ka1 is very large. Ka1 is very large. That means sulfuric acid completely dissociates to give H plus and bisulfate. Ka2 is 1.2 into 10 power minus 2. Therefore, bisulfate will not undergo complete ionization. Bisulfate comes under weak acid. It is weak acid, whereas it is strong acid. So sulfuric acid we can say strong acid, whereas bisulfate we can say weak acid because Ka is 10 power minus 2. Sorry. Sulfuric acid is low volatile. Volatility is less. Why volatility is less in the sense? It is having hydrogen bonding, intermolecular hydrogen bonding. Therefore, volatility is less, we can say. So, due to this one, it is used for preparing more volatile acids from their salts. Now, if we will take HF, HF is a gas, HCl is a gas, HF is gas, HCl is gas. So, transporting HF and HCl is difficult, but transporting HF and HCl in the form of salt is easy. In the form of salt is easy because they are solid. So, HF and HCl, transporting HF and HCl, instead of that, transporting their corresponding salts is easy. Now, this salt we have to convert into HCl by treating with what? In the sense corn sulfuric acid. So, on treating with corn sulfuric acid, we are getting HCl gas. Similarly, on treating with corn sulfuric acid, we are getting HF. Therefore, this sulfuric acid, low volatile acid, is used for preparing high volatile acid from their salts. Okay. Then corn sulfuric acid acts as a dehydrating agent. Corn sulfuric acid is acting as a dehydrating agent. We'll take sugar. To this sugar, let us add corn sulfuric acid. What happens means corn sulfuric acid takes away all the hydrogen atoms and oxygen atoms in the form of water molecules. Corn sulfuric acid absorbs all the hydrogens and oxygens in the form of water molecules. What is the rest means? Carbon is rest. Carbon. So this is called charring of sugar, we will say. Charring of sugar. That means sugar is burnt off. like this, chairing of sugar. So corn sulfuric acid on adding into sugar, sugar becomes carbon particles because all the hydrogen atoms and oxygen atoms becoming water molecule which is absorbed by corn sulfuric acid. Therefore, corn sulfuric acid is acting as a dehydrating agent, we can say. Then, whenever we are handling corn sulfuric acid, we should see that corn sulfuric acid should not fall over our skin. In the laboratory, in the salt analysis, we are using corn sulfuric acid. In the laboratory, we are using corn sulfuric acid. That corn sulfuric acid we have to handle properly using dropper tube. It should not be fallen over our skin. Over skin, it should not fall. If it falls, what happens means it will burn that part. It will burn that part. That part will become completely burning sensation. That part will get a completely burning sensation, and that part will become completely black. That skin will be removed completely, depending on the quantity of corn sulfuric acid. Therefore, corn sulfuric acid we can say very corrosive over skin. Very corrosive we can say. Why corn sulfuric acid is very corrosive? Sir, the skin is made up of hydrogen atoms and oxygen atoms, water molecules and all is there. Corn sulfuric acid absorbs water molecules from the skin. Absorbing water molecule, that means due to affinity it is absorbing water molecules. Due to attraction it is absorbing water molecules. Attraction means energy will be liberated. So lot of heat will be liberated. Lot of heat is liberated means temperature becomes high. Therefore, we are getting burning sensation. That burning sensation will be lost if that part is washed with the sodium carbonate solution. So we must handle corn sulfuric acid very carefully because it is very corrosive over skin. Okay. Then corn sulfuric acid act as oxidizing agent. That reactions we will see. Corn sulfuric acid converts copper into Cu2 plus, while corn sulfuric acid becomes sulfur dioxide gas. Corn sulfuric acid converting copper into copper ion. This copper ion takes sulfate and becomes copper sulfate. Sir. Corn sulfuric acid converting sulfur into sulfur dioxide. Corn sulfuric acid becomes what means sulfur dioxide. Okay. Corn sulfuric acid converting sulfur into sulfur dioxide. Corn sulfuric acid converts carbon into carbon dioxide. Like this we can say. Next step. We will take potassium bromide. To this we will add corn sulfuric acid. What happens we will see. So Br minus takes H plus and becomes HBr. What is the remaining means KHSO4. This HBr with the corn sulfuric acid, we are getting Br2. Sulfuric acid becomes sulfur dioxide. Bromine is -1 here. Here bromine is 0. So -1 bromine becomes 0 bromine. Oxidation. So it is undergoing oxidation, whereas sulfuric acid is undergoing reduction, we can say. Similarly, if you take potassium iodide, you will get I2. Okay. So with the corn sulfuric acid, you see that F minus with the corn sulfuric acid gives only HF. Cl minus with the corn sulfuric acid gives only HCl. Br minus with the corn sulfuric acid gives HBr, which immediately converts into Br2. So remember that Br minus with the corn sulfuric acid, we are getting bromine Br2. Similarly, I minus with the corn sulfuric acid becomes Hi. Hi immediately becomes I2. So with the corn sulfuric acid, how halides are involving, you see, F minus converting into HF, Cl minus converting into HCl, Br minus converting into Br2 bromine, I minus converting into iodine I2 with the corn sulfuric acid. Okay. So corn sulfuric acid is used as a oxidizing agent, we are saying. Then uses of corn sulfuric acid. It is used for manufacturing fertilizers, ammonium sulfate, superphosphate, like this. Then it is used in metallurgy for cleaning metals before enameling. So metals will be taken for a enamel coating. Before enamel coating, the metals will be cleaned with corn sulfuric acid. Then electroplating. Metals will be taken for electroplating. Electroplating means coating one metal over another metal. Generally, gold metal will be coated over some other metals. Silver is coated over some other metals. Like this is called electroplating. For electroplating, it is used. For galvanization, it is used. Then it is used in lead storage batteries. In the lead storage batteries, if you see, concentrated sulfuric acid will be there. Then it is used as a laboratory reagent. Okay. Then we will see sodium thiosulfate, IPO solution we'll see. We'll go for IPO. This IPO is a commercial name. Chemical name is sodium thiosulfate. Sodium thiosulfate. What is the formula for this one? Na2S2O3.5H2. So its name is sodium thiosulfate pentahydrate, we can say. Now preparation of IPO we'll see. We are taking sodium hydroxide. To this we are adding sulfur. Sulfur is solid. Sodium hydroxide is aqueous solution. It is the contents are boiled. We are getting IPO solution. We are getting IPO. Na2S2O3. IPO we are getting. Then we are getting a Na2S and water. So we are getting a IPO. We are getting properties. This IPO, where it is used in the sensor, it is used in the photography. So this IPO is colorless crystals. Colorless crystals, we can say. This IPO is a fluorescent salt. What is meant by a fluorescent? This on exposure to air, the hydrated water molecules will evaporate away. Then it will become anhydrous. So a fluorescent salt means the hydrated water molecules evaporating on exposure to air. So hydrated water molecules evaporating on exposure to air means efflorescent, we can say. Then how it is used in photography, that we'll see. How it is used in photography, that we'll see. Now we will take photographic film. We will take photographic film in the sense black and white photo. That film we will take. In this film roll, it is coated with what means silver bromide. It is coated with silver bromide. This is completely coated with silver bromide. Now, this it is there. We are taking photo. Photo we are taking means what we will do means here camera will be there. Here we have to pass light. Here light. So light is striking this and reflecting. Reflecting means coming to camera. So to which part light comes, that part, in that part silver bromide becomes silver. So this part is silver now. Remaining part is silver bromide. So where silver is there means this is silver, this is silver bromide. Remaining part is silver bromide. Okay. So where silver is there, here this is silver, because silver bromide undergoes photochemical decomposition to give silver in the presence of sunlight. So silver bromide undergoes photochemical decomposition to give silver and bromine. So this part has become silver. Then this photo is taken. Then this film roll should be taken out from camera in the dark room. Then it is this film roll is dipped in IPO solution. IPO solution. So IPO solution we are taking Na2S2O3 IPO solution. This film roll is dipped in this IPO solution. It is doing what means it is combining with the silver bromide. It is combining with the silver bromide to give a complex. The complex is Na3Ag S2O3 twice. S2O3 twice. This complex is soluble in water. It goes to solution. Then NaBr we are getting. NaBr also goes to solution. NaBr also goes to solution. So that this silver bromide goes to solution. It is washed away. Now after silver bromide is going away, What is there means only silver. This part alone is there. It is silver. Here silver and all is not there. Here silver bromide and all is not there. This is called negative. Okay. So this hypo solution is used in photography. This hypo solution dissolves silver bromide by forming complex. This is called sodium argento thiosulfate. Okay. Then other chemical properties we will see. Sodium thiosulfate Na2S2O3 we will take. To this we will add silver nitrate solution. Silver nitrate solution. This solution is what in the sense a dilute solution we will take. Now what we are getting in the sense now what we will get, that we will see. This hypo solution is colorless. Silver nitrate solution also colorless. Now you take that test tube. Take silver nitrate solution. Add hypo solution. Immediately you can see white precipitate. That white precipitate immediately converting into yellow color, then converting into brown color, then converting into black finally. Okay, so how the color change takes place, you see, you are taking silver nitrate solution in the test tube, you are adding hypo solution, all are colorless. On adding hypo solution into silver nitrate, you are getting white precipitate. That white precipitate quickly changes into yellow color, which changes into brown color immediately. That changes into black finally. This color change takes place within few seconds. Okay, sir. Now this hypo with the silver nitrate, what happens we will see. This Na plus and Ag plus will be replaced now. In the place of Na plus, Ag plus comes. So we are getting Ag2S2O3, silver thiosulfate. Then NaNO3 we are getting. This is white precipitate. The silver thiosulfate is white precipitate. This white precipitate becomes yellow color. Then it is becoming brown color. Then finally it becomes what in the sense black. That black is what in the sense Ag2S. That black is what means Ag2S precipitate. Silver sulfide, Ag2S, black precipitate. Then another substance we are getting sulfuric acid. How? Why we are getting sulfuric acid? Because thiosulfate formula we will write. Thiosulfate formula we have discussed like this. Thiosulfate formula is S2O3 2 minus. It is thiosulfate. This sulfur, if you replace the sulfur by oxygen, then it is sulfate. Therefore, sulfuric acid. So this thiosulfate with water, sulfur is replaced by oxygen. Therefore, sulfuric acid. That sulfur becomes sulfide, Ag2S, silver sulfide. Okay. Next chemical reaction we'll see. Sodium thiosulfate will take Na2S2O3. We'll take silver nitrate solution. Now this is concentrated, hypo is concentrated. Now what we are getting means we are not getting white precipitate now, we are directly getting complex. The complex is Na3Ag S2O3 twice. This complex we are getting. Then that means Na plus is replaced by Ag plus, therefore we are getting this complex. Then we are getting NaNO3. Okay. Next, the sodium thiosulfate is combining with the chlorine in the presence of water to give Na2SO4 plus HCl and sulfur. This thiosulfate we will write. This thiosulfate formula is like this. Thiosulfate formula we have written. Now we will write oxidation numbers for this -2, for this +6. Now what happens means this -2 sulfur becomes 0 sulfur precipitating. In this place of sulfide, oxide comes, therefore it is sulfate. That sulfate we got. This sulfur undergoes oxidation. Therefore, this Cl undergoes a reduction. See, 0 oxidation number becomes -1 oxidation number. Okay. Now, this reaction is used in textile industries in order to remove excess chlorine. So, to remove excess chlorine, this hypo is used. Therefore, this hypo is used as anti-chlor in textile industry. We can say anti-chlor, like this. You can say. Next, this hypo chemical properties will continue. Hypo reacting with iodine to give what means sodium tetrathionate Na2S4O6 and sodium iodide. Okay. This reaction, where it is used, in the sense it is used in volumetric analysis. It is used in volumetric analysis. In the volumetric analysis, this reaction will be this we will take in the burette, this we will take in the pipette solution, that means conical flask solution. So we will do titration. Using titration, what is the number of moles of iodine? We can find it. Why to find the number of moles of iodine? Because it is used for estimating ozone. If ozone is how much is there, to estimate that, what we will do in the sense this iodometry method we will use. In the iodometry method, iodine will be liberated. The liberated iodine is treated with the sodium thiosulfate. Then we can find what in the sense number of moles of iodine we can find. From the number of moles of iodine, we can estimate ozone. We can say how much amount of ozone is present, that we can say. So for that case, this is used. So how this reaction will be done, that we will see. We will take ozone. This ozone is treated with I minus aqueous. I minus aqueous means potassium iodide. You take potassium iodide solution, you are taking ozone gas, you are passing. What happens means ozone is becoming O2, I minus becomes I2. Now see, you are taking potassium iodide crystals, so you know the concentration of this solution. Otherwise, you leave it. You take potassium iodide solution, pass ozone gas, you will get iodine. How much iodine we got, that you titrate with hypo. So from the number of moles of hypo, we can say number of moles of iodine. From the number of moles of iodine, we can say number of moles of ozone. This is called a iodometry. Like this, we can say. Now we can estimate ozone, we can say. So for the estimation of many things, this iodometry is used. Iodometry means this iodine will be liberated. That liberated iodine will be treated with a hypo solution. So we can use this reaction in the volumetric analysis. So hypo is used for estimating iodine, we can say. Next reaction we'll see. Hypo we are taking. This hypo we will treat with ferric chloride. We are getting what in the sense this Fe3 plus and Na plus will be replaced. Therefore, we are getting ferric thiosulfate. Ferric thiosulfate we are getting. Thiosulfate formula is S2O3 2 minus. Ferric is +3. So cross multiply, you will get ferric thiosulfate. Then you are getting NaCl. This ferric thiosulfate is violet color. Okay. This ferric thiosulfate, in this ferric thiosulfate, ferric is undergoing reduction and becomes ferrous. Therefore, this violet color disappears. While the thiosulfate S2O3 2 minus becoming tetrathionate S4O6 2 minus. Tetrathionate S4O6 2 minus, we can say. So ferric is undergoing oxidation, sulfur is undergoing reduction. Sulfur is undergoing reduction. So thiosulfate becomes a tetrathionate, we can say here. Then this sodium thiosulfate hypo is used in the extraction of silver and gold from their ores. In the cyanide process, we will say this silver is extracted, gold is extracted from their ores using this hypo. This hypo is used in medicine, we can say.